All right, so our tour of the solar system and galaxies and how things are and where things are is almost at an end. But there are messages being sent to us about how and the way the universe works. And some of them are going to be a little spooky. Now, I'm not going to go completely down the spooky road because there's plenty. You go buy a book, a physics book at the bookstore, you'll find plenty in there that will confuse you and make your life seem less steady. Instead, what I would like to do, I talk about one very specific item, and it has to do with Albert Einstein and gravity. See, we have never yet described what gravity is. Remember, Newton thought it was elastic bands holding the things together. Well, that's just silly. Because invisible elastic bands holding them together, or like the invisible elastic bands holding these things together. We know that's not true. And so then the question is, what is true? Right? What is actually going on? Well, masses are just naturally attracted to each other. Don't worry about it. Well, that was the theory all the way up to the 1918-ish land. But there was a problem. There was a problem with gravity, and it involved a cute little thing, and I'll tell you the rest of the story too. Albert Einstein was invited to a conference to talk about special relativity. What you don't know about special relativity, special relativity is where Albert Einstein said, you cannot go fast at the speed of light. So therefore, for about 6 years, about early 1900s to about 1918, he was making this argument that you can't go fast at the speed of light. Well, one professor thought they'd figured out how to prove he was wrong. So this is how he went about it. He said, look, so first of all, he invited Einstein to a conference, then he was going to do the introduction. His introduction should be, hey, it's great. We have Einstein here. He's a Nobel Award-winning physicist, and he's doing research on this and this and this. He's also may have heard of relativity. That's what he should be saying. Instead, what he does, he says, hey, Albert Einstein's wrong. Look at this. Here's the sun. Let's imagine the sun's right here. Let's see the Earth's right here, right? We know in order to go in a circle, there must be a center-seeking force. Yeah, we also know it takes time, 7 or 8 minutes, to get from the sun to the Earth at the speed of light. If nothing goes fast at the speed of light, force can't either. And so therefore, if the Earth moves during these 7 or 8 minutes, then the problem is the sun should pull it this way because it thinks the Earth's here, would end up pulling it this way. And you're thinking, oh, it's 7 minutes out of a whole year, Mr. That's pretty close. And it is pretty close. But it would be noticeably different. The Earth would have a kind of wobble to it. It would go around the sun like this. And it doesn't. And so he went on to describe how if relativity really works, if nothing can travel faster than the speed of light, then gravity wouldn't work and the Earth would be wobbling like this. And so the Earth doesn't do it. Mr. Einstein, you're wrong. And now I'm interested in Mr. Einstein coming to the podium. Now, everyone's watching Einstein. Einstein at the time looked like he had no idea what the guy was talking about. He's looking at the audience. He's waving at the audience. He's he's got a coat button that he doesn't quite have right. He's trying to figure out how to get that coat button together. And then he gets introduced, gets up there. He says, I want to thank the host for those kind remarks. And in fact, he gave the perfect introduction to something I was thinking about. And I wasn't really planning on discussing it now, but you know what? Let's discuss it now. And he laid out a new theory for gravity. He recognized this problem. He said you can't instantaneously send information back and forth. The information already has to be here. So he thought, you know what's really happening is the star, the sun, is sitting in the field of space. And because it's got mass, it is bending it down like it's sitting in a trampoline. And the Earth bends itself down when it gets there. And so the Earth is rolling around this funnel made by the dent caused by the sun. That gravity is really the denting of space. And space itself is bent. Not just that it acts bent. The space actually is bent by having masses in it. Which means the Earth, which must travel in a straight line according to Newton, is trying to travel in a straight line, but since the Earth is curved, it just follows the curvature, thinking it's going in a nice straight line. That is what's causing the force, use quotation marks, force, that Sir Isaac Newton was talking about. So a picture that looks more like what he was trying to get at would be this one here. No, not that one. It would be this one here. This is what he thinks is going on. And because of that, if you see this picture in the back, you see how it says real back there? That's the real object. And as the light approaches the object, it starts hitting the corner of this curve, and that corner of the curve would cause it to bend and get up down here. So the Earth would see the star where it shouldn't be. It would look like it's over here. So drawing it myself, it would look like, so here is something like a galaxy in our way. And then we've got some sort of object here. And then here we are on Earth, minding your own business. Light travels towards this thing. It should end up over here, but instead it bends and then turns towards us. And then we think that's this object. Let's make it an E. Let's say this E is over here. And then, by the way, light's coming around this way too, right? And so that would bend, and then it would hit here. And so sitting here, we'd observe, oh, that clearly came from over there. Well, this is the real object. These are two images we'd see in the sky because it's behind this and the light is being bent. So when Albert Einstein was asked, how would you test such a thing? He said, oh, it's easy. You just have to find two identical stars on opposite sides of a massive object. Then you know it's a real object sitting behind it. And then, okay, good luck with that. Turns out, didn't take long. There's a set of astronomers who got themselves the Nobel Prize because they swept the skies for something specifically called a pulsar. Pulsars are really dark, dense stars that are spinning. And as they spin, they have a magnetic field. That magnetic field pulls the electric charges around it. Those electrons being pulled around it send a radio pulse. So this thing beeps every so often. If you have a radio receiver, if you have a radio tuned to the right channel, you'll hear a beep, beep, beep. Now, what's fascinating about pulsars is pulsars are in space. They're unaffected by things like friction, so they're the most accurate clocks in the universe. And by the way, you can buy a watch called the Pulsar because of this very name brand. And the bottom line is these things are accurate to 0.000000 right here. That's how accurate they are. The most accurate clocks, in fact, our atomic clocks aren't as accurate as they are. And so these pulsars, as they're beeping, 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 they're all different beeps. Every one of them has their own signal. But if you take a radio telescope, there are certain ones you can hear the exact same guy, whether you put it here, pointed that way, or you point it here, pointed that way. You get the same pulsar, which suggests that Einstein's right. Now you're thinking, oh man, drawings, pulsars, you didn't. Good news for you is 20-something years ago, they got you a visual version of it. Visual, all right. Here we go, visual version of it. I can't get to the visual version of it. That's just terrible. Come on. Come on. Oh, this is terrible. This is terrible, 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 terrible. Sorry about the slowness here. All right, let's try this. And so here you have something very interesting. These are quasars. Quasar, 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 quasar. They're the same quasar. They look exactly the same. Here are galaxies. Same number of stars, same number of spinning direction, same amount of redshift. 3 different places in heaven. In this area here somewhere is a very dark object which is bending the objects around it. Now, what's really kind of cool about this is I had a student years ago say to me, well, if there's a dark object here, wouldn't I see stars on like a circle around it? Well, it'd only be if you were perfectly aligned with it. If something was directly behind it, you'd see it smeared. You'd actually see a smear star all the way around it in every direction. And that would be super cool, but as far as I know, the odds of that you'd be able to see that are almost zero on man. But there are a lot of stars, right? So if you looked long enough, you might just see... Seriously, I'm not going to get that either. Oh... You might just see this. This is a galaxy. Behind it is a bluish galaxy. That bluish galaxy, the light is coming and bending to our eyeballs from all the different directions around this one galaxy. This is the same galaxy, but a galaxy this big, taken in this front, would be, it's hard to describe how big it would be. It would be billions of light years across, which would make up most of the known universe. That's not what's going on here. What's going on here instead? What's going on here instead is there is a galaxy behind there. This piece looks just like this piece. This piece down here, this all looks like copies of the same thing over and over and over. Same stars in that same pattern. This is behind this galaxy. There is another galaxy, and we're seeing it as this light bends around the star and comes back to our eye from every which direction, three-dimensionally. So, what is gravity? Gravity is the denting of space. A long time ago in class, I said, Miss Reed, you're denting the space around you. That's why things are attracted. You're bending, you're warping space because of your massiveness. Everything in the universe bends the space around it. For the most part, it's unnoticeable. It's incredibly small. Things don't roll together very often. But you are warping the space you're in. The very X, Y, and Z dimensions are curving because you're standing in it. And that's true for you, that's true for galaxies, that's true for light going through it. Anything with mass bends the space around it. And so, it is indeed true that you, whoever happens to be listening to this video, are currently bending the space around you. And that's why things are attracted to you. All right. Gravity is a warping of space.